So I'm Brendan, and I'm a developer advocate at RSK. A little bit about myself. I'm from Singapore. Most of my background is working with JavaScript and Node.js. I run a tech meetup called DApps Dev Club, and it teaches, I guess, how to make a decentralized application. And I'm also currently learning Spanish. Yep. Okay, so what are we going to do today? So we're going to be talking about what is a DApp. We're going to be talking about smart contracts, the Solidity compiler, the Ethereum virtual machine and the RSK virtual machine remix, and then finally we'll end off with a hands-on on Solidity by feature. So this is where we will be looking at some code. So a decentralized app consists of three components. One is the smart contract, right, which is our focus for today. And then there's also a Web3 enabled front end. So that's basically a web application, or a native application that knows how to talk to or interface with the blockchain and the smart contract. And then there's also another component called decentralized storage, and that's where you want to store data that's larger than what you would typically store in a smart contract. So that's where things like IPFS and Swarm come in. Yeah, so those are the three things that a DApp is comprised of, and today we'll be focusing on smart contracts. So smart contracts are deployed to the blockchain, and they comprise of two things. The first is executable code, and the second is data or storage. So the code inside of a smart contract is immutable, meaning as soon as it's deployed, it never changes after that. But the data, on the other hand, when it's deployed, it starts off with initial data, and then that data can change. And in order to do that, right, you need a signed transaction. So the data that's stored within a smart contract is owned by that smart contract. So in order to change that data, what needs to happen is there needs to be a signed transaction that interacts with the smart contract in some way, and that executes the code in the smart contract, and only that code is allowed to modify its data. So not all function invocations on a smart contract do modify data, so it's optional. So if you do, however, if you do need to modify data, you do need a signed transaction. Then also these smart contracts, they're executed on computers that are running the blockchain software. So for example, if someone's running an RSK node, right, that incurs a computational and storage cost on that node. So they get compensated, denominated in RBTC, and that is paid for in gas fee. So each time you execute a certain instruction, it's added to a running total, and then that amount is your gas fee. And gas is just basically a fraction of like a very small amount of the native currency of that network. So in the case of RSK, you have RBTC, and like a tiny amount of RBTC is paid for each function call. Yeah. So we'll take a look at that in a bit more detail. It'll be more clear. It'll be clearer when we take a look at the code. So then we have SolC, which is the Solidity compiler. So it takes in a Solidity file or multiple Solidity files, and then it outputs two things. One is EVM bytecode. So this is the code that actually gets uploaded into the blockchain and gets executed in the blockchain. And the second thing that it outputs is something called an ABI, or Application Binary Interface. So that tells a Web3 enabled front end, within this bytecode, how do I actually know what functions exist, and what their parameters are, so on and so forth, so that it is actually possible for this executable bytecode to be interacted with from the outside. Now, do not get intimidated by this. So this is a smart contract that we'll be doing later on, and I just wanted to show you what the outputs are like. So on the left here, this is the EVM bytecode. The bytecode actually is just pure hexadecimal, but I thought that would be even more crazy to put on the screen. So this is the actual opcode versions of the bytecode. So you can see the first instruction is to push this hexadecimal number into memory, so on and so forth. And you're talking about pushing individual bits and bytes into and out of memory and into and out of storage, and moving the instruction counters, so on and so forth. So it's very similar to assembly, but it's not assembly. It's its own thing in that sense. And then here on the right here, we have the ABI, or Application Binary Interface. So here we can see that, all right, so we have like all of these various things, and then we have like a method here. Here are things, so it says here are all the functions, essentially, here are the parameters, and here are all their types. And here's the type of the return values for each function. So based on this, right, the Web3 front-end client will know how to, or where to, which parts of the code inside the bytecode need to be executed for a particular function. Yeah, so that's just a little peek under the hood. We won't be going to that level of detail in today's talk, just so you know, it's just an FYI. So next up we have the Ethereum virtual machine. It's a stack-based virtual machine. Now when I say virtual machine, I am not referring to Citrix or something like that. It's a different thing. It's more similar. If you've heard of Java, Java executes on a virtual machine, which is why Java applications can run on many different operating systems and many different hardware configurations using the same compiled binary. It's because of this virtual machine that executes Java bytecode. So the EVM also has its own bytecode, which you saw earlier on, and in particular, it's a stack-based virtual machine, and we'll take a look at what that means later on. It is also quasi-Turing complete. So you may have heard this term Turing complete, and what that means is that it is technically possible to write any program you wanted to. And that is made possible by the fact that it has a complex enough instruction set to enable that. And there's like a whole bunch of computer science definitions about that. And one of those things that's important to know is that if you have a Turing complete machine, it is possible to write a program which runs indefinitely, runs forever. And we don't want that in the case of blockchain, because then anyone who's mining smart contract executions is setting themselves up for basically a denial of service attack just by through a malicious transaction. So that's why we have this term quasi in front of it. That's basically saying that when you execute a function on a smart contract, it can run out of gas. And if it runs out of gas, it doesn't matter if the instruction set says to continue, it is just going to abort and return an error. So that function will not complete because the transaction has run out of gas. So a bit more detail on that is when you call a transaction, you specify the maximum amount of gas that you're allowed to specify, so the max limit or the ceiling of it, and a transaction will consume up to that amount of gas. And if it goes over that amount, the transaction is considered to have failed, and you don't get your gas back. The miner gets it. And the miner is free, his resources are free to continue executing the next transaction. So then it becomes in the interest of the person calling the smart contract to ensure beforehand that that doesn't happen and that the transaction and the gas fee that they pay is actually worthwhile. It's also comprised of low-level opcodes, which you saw earlier on. So you're pushing bytes of memory into and out of memory, into and out of storage, that sort of thing. Now, RSK also has a virtual machine called RVM, and it is compliant or compatible with the Ethereum virtual machine at a bytecode or opcode level. So each time a new opcode is added to the EVM, the RVM also adds that new opcode. So, so what that means is that when you use this, when you write your smart contracts in Solidity and you compile it with Sol-C, that same the same outputs, the ABI and the EVM bytecode, you can use that same thing and you can put it inside and run it on RSK and it will work just fine. So next up, we're going to do a step-by-step illustration of the, let me just refresh this perhaps. Okay, so here we go. So we have an illustration here, and this box here represents a stack. So each time you put something inside of it, the next thing goes on top, right? And then certain instructions cause the items inside to decrease. And we'll see what I mean by then. So it goes up and down like a stack. That's why they call it a stack-based virtual machine. So the first instruction is push 1. And if you take a look at what that means, it says push one item onto the stack. And it just so happens that the next thing is 4. So you're going to do that, right? Then the next instruction in the EVM bytecode is push 1 again. So push 1 byte and the number is 3. So we're going to put 3 on. Then the next one is push 1 for the number 2, and we're going to do that. So at this point, our stack has built up. So it's got a 4, followed by 3, followed by a 2. Now the next opcode is mul. That stands for multiply, and the implementation of that that multiply is actually pop 2 items off the stack. So it'll take this one, and then it'll take this one, and then it'll actually do the computation. So it'll work out that those numbers are actually 6, and then it pushes the result, which is 6, back onto the stack. So that happens. So just to go backwards, we had 4, 3, 2. When multiply gets executed, we now have 4 and 6. 6 being the result of the multiply that just occurred. Likewise, now we have add, right? Add is to sum 2 numbers together. We pop 2 items off the stack, 6, 4, multiply, add them. Sorry, there's a mistake here. And then the result is 10, right? And then that result is pushed back. So these 2 will be taken out of the stack, and in its place there will be a 10. Very similar to the multiply. And then we have pop, right, which is just to take the item on the stack and return it. And so the result there is hexadecimal for 10, and then that gets returned. So in essence, we saw how this set of instructions here, push 4, push 3, push 2, multiply, add, pop, basically means 4 times 3 plus 2, and then you get the result. So that's a very simple demonstration of how a stack-based virtual machine works. This instruction set here is actually EVM opcodes. So that's essentially how you make sense of this, where was it? This crazy thing here, right? That's actually what's happening on the hood. Of course, there are many more opcodes than the ones that we just saw. This is just a very simple subset. That was actually just a very simple subset for demonstration purposes. So let's go back to this. All right. So next up we have Remix. It is an integrated development environment, and it's completely online, web-based inside your browser, so you can just open it and get going. And it's also an all-in-one tool, so it allows you to edit code. It contains a compiler, Sol-C, well, more specifically, it contains Solc.js, which is a pure JavaScript implementation of Solc, but it's good enough for most use cases. It also contains a blockchain simulator. So this is similar to what you get when you run Ganache, which simulates a blockchain locally, completely in memory, without actually having to run a node that connects to a real network. It just gives you all the it just pretends to be a blockchain, and therefore transactions are instantaneous. You don't have to wait for consensus and all that. Very good for doing development. It also contains the ability to do two things with a compiled smart contract. You can deploy it to either the simulated blockchain or to a real blockchain. It's up to you. And if you want to deploy it to a real blockchain, you need to have something like MetaMask or Nifty Wallet, which provides you with a Web3 provider that's able to connect to these external networks. And it also, once you've deployed a smart contract, you also have an auto-generated user interface. So what it does is it takes a look at each of the things inside the ADI. So it knows what all the functions are and what all the parameters are and what the return values are. And it generates a form where you can input the values in and execute them, like send them to the blockchain. And we'll try that out later on, maybe if we have some time. This is what the Remix IDE looks like. But we'll actually get a chance to play around with it later on in this session. So next up we have Solidity by feature, and this is where we'll be doing a hands-on part. So we're going to be covering, I would say, just the basic parts of Solidity. There's a lot more to Solidity than just this, but this is good enough to do a lot of things in smart contracts. So first off, we'll look at what the structure of one is. Then we'll look at base types or primitive types. So that's things like integers and bytes. Then we'll also have reference types like structs, maps, and arrays. Then we'll have functions and modifiers and events. And in order to bring us through this, I have a demo which like sort of shows you a sample smart contract, which you'll step through one at a time. So we'll start off with structure, and then we'll add base types, and then we'll add reference types, so on and so forth. So we'll get to the end, and each step you can see exactly what is the difference, like which new lines have been added or deleted between one version and the next. So now it's time for a hands-on. So what I'd like everyone to do at the moment is to go to this page, right, which I am going to share in the chat. So pad.riseup.net/p/inside Solidity BGUIZ. So that's the oops, sorry. Share that again. So this link will bring you to this page here, which I'll make slightly bigger so that it's easier to read. Now, this contains a link to the slides that I've just shown everyone earlier on. It also has a link to the EVM-based stack execution diagram, illustration, which I showed you, which I went through earlier on. It also has a link to Remix, which I'll need you to open now. So right now I have Remix loaded up in Chrome already, right? Yeah, so use this exact link. Don't just type remix.ethereum.org. I need this particular version of it so that we get the exact same Solidity version 0.5.0. So that will do that for you. And then also have this link, which we haven't looked at yet, which is this, and we'll be doing this with a remix side by side. That's the hands-on component for today. Okay, I'll just give everyone a moment. What you need to do is you need to open up this link, and you also need to open up this link, preferably in two separate tabs or browsers so that you can see them side by side, similar to what I've got set up here. All right. All right, I hope everyone is ready. All right, let's begin. So the first thing that we should do in Solidity, in Remix, sorry, is to make sure that we are using like Solidity. There's more than one environment. It used to default to Solidity, but now you've got Viper and potentially others. So click on Solidity and you'll notice that there's a couple of new things, or more than a couple of new things that have opened up in the side. The main one here is Solidity compiler, and this one is deploy and run transactions, so on and so forth. So you've got a bunch of new things that are enabled once you click that. So now you can go ahead and close this tab. Click on the second icon from the top on the left nav bar and the vertical nav bar, File Explorers, and hit this plus button here. And let's just call it cars, C-A-R-S.sol, because that's the theme that we'll be going with this particular thing, demonstration. So here we have cars.sol. Now I'll go ahead and do a mixture of copy pasting as well as typing out. So and you can go ahead and do the same. If you don't want to do it step by step, then just copy and paste like so yeah, just the orientation. The left side here shows the difference. So from when we from one step to the next, what actually has changed, and you'll highlight the difference. And this shows the state of the contract in full, so the exact file that you need to compile. So just as an example, we started off in step 1. This is step 2, and you can see here, okay, so this green part here means that we have added these lines here, that sort of thing. And then here, the red parts mean that we have deleted these bits and replaced them with these green bits. That's basically what this aims to illustrate. So you can choose to do follow along by typing the commands, the new things directly, and trying it out yourself. And I'd highly encourage that if you do it in your own time. But for maybe in the webinar, if that's a bit too fast for you, then just go ahead and just copy paste everything from the right hand side. So what I'm going to do is I'm going to do pragma. So what that means is it's telling you which version of Solidity that you are supposed to use. And you can see here inside the Solidity compiler thing, I've selected 0.5.0, and that matches this one. This thing here actually means you can use any version higher than this. So you could use 0.5.1, for example, but for now, let's just stick to this. Let's go back to file edit. The next thing we're going to do is we're going to define a contract. And we'll give it a name, and that's it, right? So that defines a contract which does absolutely nothing. Then we create a constructor, which is, if you're familiar with object-oriented programming, is what initializes a class. You can think of a smart contract as similar to a class, and perhaps more specifically, you can think of it in most of the time it is used as a singleton class, meaning it's only ever instantiated once. Although you can go ahead and instantiate multiple copies of the same smart contract should you desire. But most of the time you have one smart contract and there's only one copy of it. All right, so now we'll go over here and we'll press compile cars.sol. interesting. All right, I'm going to switch to a much later version of the Solidity compiler. Wonder why I didn't do that yesterday. Okay, so just in case you encounter the same error, what I did was I switched to the latest version of Solidity 0.5, which is 0.5.17, and I'm just going to copy that and paste that inside here so everyone gets that link. All right, so then when you press compile, you should get a green tick over here, which means that you can, in theory, deploy it. You'll notice here that when I click on deploy, it's selected by default a JavaScript virtual machine. So that's right now, it could be anything. It means that you're not really deploying to any network at all. It's running completely in memory on your computer. It's not connected to a cryptocurrency network at all. That's what I meant by the simulated virtual machine earlier on. But we'll come back to this later on. So let's go ahead and so we'll click on this thing here. It says deploy and run transactions. It is the fourth from the top on the vertical map menu on the left, and you click on deploy. And you should see deploy contracts, cars at, and then it'll give you an address. But the address is kind of, you can't really go to a block explorer, for example, because it's all in memory. So you can see over here, there's nothing. You know, there are no methods available because you haven't defined any. And we'll get back to that later. So let's switch back to this thing, and we'll move on to base types. So what's happening here is that we're adding a bunch of, we're defining what's inside a car, right? What are the properties of a car that we would like, right? I'm just going to go ahead and copy this section here, and we'll put it above the constructor. Let's fix up that alignment. Okay, so just an orientation, uint stands for unsigned integer, and the number after that is a number of bits. So yeah, so these are a bunch of numbers: the number of doors, the distance the car has traveled, its coordinates, yeah, and then byte 3 means 3 bytes used to store a color. Now over here, let's put a, just so it's clearer, we have a type called enum. So this isn't actually I guess a variable, right? It's just a definition of an enum, and then it's called status, which can be either driving or parked, and then status is actually is used as a type here. So you're defining a type for enum, and if you look at that, it says, okay, so now I have a status which can either be driving or parked. Now, if you take a look at what the Solidity compiler does under the hood, this basically just translates the numbers. So driving is 0 and parked is 1. But the Solidity compiler gives you this as a usability or readability thing. And it also gives you some compile time checks. So for example, if you decided to use an integer to store the value of status and you assigned it a value of 2, the compiler is not going to know that that was a mistake, and it's not going to warn you about it. But you can't do that in status. So if you assign status to something else other than driving or parked, it will just say no, sorry, you can't do that. All right, and finally we have address, which is the address of the account, which we are going to call owner. So whoever creates this contract is going to be called the owner, and we're going to store their address here. All right, so right now our smart contract still doesn't do anything, and if you don't believe me, let's do a compile, and then we go to deploy, we press deploy, and we'll see, we'll delete the previous instance, and we'll see this new instance, right? It has values, right, over here that you can query, and all of them are just going to be 0, but there are no methods. There are no methods to actually set these values, for example. So if you get color, you'll get 3 bytes that are all zeros. If you get doors, you'll get a single integer that's 0, so on and so forth. Like everything is going to be 0. Even the owner address is just going to be a big long 0 or null address. All right, so let's just destroy that copy of the contract and we'll go back to editing the file. Now let's create some reference types. So what we're going to do is we're going to move the enum to the top to get it to separate it, I guess. And then we are going to create a struct. A struct is a grouping of several variables together, so that they're stored in memory in a way that you can reference them all together. And then what we're going to do is we're going to copy I see. So we're going to change that to car status. Car status. It's going to rename the enum there, and we're going to put the owner together as well. All right, and then we'll put it there. Great. So now we have a struct that comprises of all of these values. So we put the enum outside. It doesn't make sense to define a enum within a struct. It won't work. But you can put variables that actually store values inside of a struct. Now, one thing you'll notice is that previously I had these things, right? So these are visibility modifiers. Anything that's public, what the Solidity compiler does, as we saw earlier on, is auto-generate a getter method for it, so you can retrieve its value by calling the smart contract. Now that we've got a struct for a car and we've grouped all of those values in a car, what that means is that we can make multiple cars. But before we do that, what we need to do is we need to realize that this car is defining a new type, right? So a type like an enum cannot have a visibility modifier. So we're going to delete that. Right? And so now we have a smart contract which has a definition of an enum type and a definition of a struct type and nothing else. So I'm not done yet, as you can see. However, what we can do is we can compile the contract again and then press deploy, and we get a new contract, and this time we don't see those buttons that we saw earlier on. We're back to where we were when we had the constructor in terms of what appears here, right? Because now we don't have any variables that are public. So, they've all been grouped inside the car. So let's just go back to editing this, and we'll actually expose, instead of a single car, which was what it effectively was, what the smart contract was effectively representing earlier on, we're going to have a, instead what we're going to do is we're going to get a collection of cars. So there's a common pattern for this, and that's like to use an integer to represent a incrementing index, as well as a mapping to store a collection of structs. So unsigned integer 256 public cars. So that's what num cars. How many typos can you make? All right, so and we'll initialize that to 0. And then we'll also create a mapping called cars. And the critical part is what we put inside mapping. So we're going to say that the key of a mapping is unsigned integer, and the value is of type unsigned integer, and the type of the value in the mapping is of the struct called car. So what that means is that we have this variable state variable called cars now, and it has a collection which you can look up by an integer, and it'll return you the value of type car, which will contain all of these attributes. That is the that's what we just done. Now let's compile it again, and then we go to deploy, and we press deploy, clear the old instance, and now we'll see that we've got two variables, right? Two methods, sorry, exposed, right? So we can press num cars, and we're expecting this to be 0 because we haven't got any cars inside. Right now we're just defining how we're storing the data, but we actually haven't put any data in it. Except for num cars, which is initialized to 0. This is a bit redundant. I'll show you over here. Actually, I'll enable auto compile so that I don't have to keep clicking inside here. So every time I press save, it'll just compile and you'll see that green tick. So you'll just do that one more time. I'll press save and you'll see that over there. Yep, it went, had a blue spinner and then it's back to a green tick. Okay, so from now on, I don't need to manually compile anymore. Okay, so so at this point, you can see I'm going to destroy this copy of the smart contract, and then I deploy a new one which I just compiled, and you can see that I didn't need to initialize num cards. It defaults to 0. So when I did that earlier on, I was just being explicit for readability purposes. Okay. So we're done at this point over here. Next thing that we're going to do is add some functions, right? So I mentioned earlier on that our smart contract doesn't do anything at the moment, right? It just is defining how we're storing the data. So now we're going to add some functions. The easiest one is, or I would say not the easiest one, but the first thing that I would do is to give you the ability to add a new car. So I will just copy and paste that and talk through it, and maybe for a less complicated function like this, I will actually type it out live. Okay, so here we have add car, right? And I've just copied and pasted the whole thing, but I'll explain what each part of it is. So this is a keyword function, and that tells the compiler that proceeding this keyword, I'm expecting a function definition, which is what you get here. The function definition comprises of a function name, a parameter list inside parentheses, modifiers over here, and the function body over here within curly braces. So in between the parameter list and the function in parentheses and the function body in curly braces, you have this over here, which is a list of modifiers. Now let's drill in one level deeper. So within the parameter list, we have a list of parameters, and each parameter is its type followed by a name, and then you can have 0 or more of them. So if you have 0, you call the function without any input, or if you have some parameters, then you have to call it with set input. So over here it says I want a color, I want a number of doors, I want a distance, I want a lat and long. So it'll be a subset of what it is here, right? Yeah. Then what it does next inside here, inside the function definition, is it says, okay, so here are the modifiers. Public means that the ABI that's generated will contain this function definition, and payable means that this function accepts some payment from the person, the account who is sending this add car transaction, and returns gives you the value of the ID of the car that was just created. So what this is saying is that someone outside of the smart contract, like let's say inside a DApp, is able to call this function, is able to pay this function a certain amount of value, and it is also, and it will return you the ID of the car that was just created if that was successful. All right, and here's the function body over here, and this is, I would say, probably the first part of the Solidity code where you're actually writing logic, if you will. So far what we've done is we've just been defining how data is laid out. This part is actually the executable code that we're writing. So the require statement saying that message.value, which is saying that how much currency was sent into this transaction, it has to be more than this amount, right? And if it's less than this amount, it will fail the transaction, saying you need to pay me at least this amount. Then what it does is it increases the number of cars by 1. So it assigns a value so what it does is it says that num cars value, I'm going to increment it by 1, and it assigns it to this variable called car ID, which happens to be the value that was returned. And then it goes ahead and creates a new car, right? So it uses a struct initializer over here like that. And that just basically accepts all of these as parameters in the exact order that it was defined as. So blah, 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 all of these things, you got it from the input parameters. And then the final two, car status and owner, it defaults it's not passed in the parameter list. It says I'm going to default to the status of parked, and I'm going to set the owner to whoever message.sender, which is whoever called this transaction. And then finally, and this is the most critical part, we update the collection of cars that we've got here. So there are actually two operations inside of this function which modify the state of the smart contract. So recall earlier on we talked about code being immutable, but data being mutable. So here we have a data mutation over here where we change num cars value. So the first time we call it, it'll be 0, and after its execution, it'll become 1. And then over here, we're saying that cars with the key of whatever the new value is, in this case 1, will be equal to a new car. And that new car is whatever we just initialized in the struct over here. And then henceforth, when this transaction is complete, it gets mined and put in the blockchain, then the state of the smart contract will be updated for this value to be 1 and this mapping to contain this the car struct that was just created. So we can see that after I save it, the compilation was successful. And now if we do a deploy, clear the old one, do a deploy, we can see that our cars not only has these two blue buttons which we had before, which is simply query the state, we also have add car. And that button's color is red because that means that you actually have to do something in order to interact with it. So then you can see, okay, so here are all the inputs that I can put in. Actually, you know what? I'm not going to do that now because I know that we're going to have to add these two functions. And then we'll do a copy with that. So we'll just destroy that copy. Notice that I'm working with the JavaScript virtual machine intentionally because I want to do these deploys very quick and fast. And then only when I have something that I think is final, then I will actually bother deploying to an actual network because it makes the iteration much faster. Okay, continuing. I'm just going to copy and paste park car as well. But as promised, I will do this function, drive car. I'll talk through it as I create it. So I'm going to do function drive car, and then parameter list, and then function modifiers, in this case just public, and then function body. So let's go ahead and fill those in. So uint256 car ID. So when you call drive car, you want to identify which car is being driven. And you also want the smart contract to be called publicly. You want that to be exposed to your DM. All right, so now we define the function body. So first we extract, so right now we have a car ID, but we need a car, right, in order to actually work out what's the logic of this thing. So we do car memory car is equal to cars brackets car ID. All right, let's walk through that. So it's confusing because there's car and car here, but this is the name of a struct. Notice a capital C. This is a lowercase c, and it's referring to a variable that's within, that's only exists within the function body of the drive car function. And memory means that this variable is stored in memory, not in storage, which, it doesn't make sense for us to store it in storage because it already is in storage. We're just extracting it so that we can make use of it. Okay, then the next thing we're going to do is we're going to create a require statement, right? Because we don't want anyone to drive anyone's car. We need to only drive our own car. So we're going to do car.owner. So whoever is calling this function, we have their address inside this special variable called message.sender. It's available in every method, and we extract that from the transaction. Solidity automatically extracts that transaction, and then what we're doing is we're saying, okay, we're going to compare it to car, whoever the owner is for the car, and if they're the same, then all good. Let's continue. But if they're not, right, we're going to give them this error message. You may only drive your own car, right? So that's great. Then the other thing we're going to do as well is we're going to require its status. So we're going to say that a car that is currently parked can be driven, but a car that is currently already driving may not be driven because it's already driving. It doesn't make sense. So car.status is equal to car status dot parked. So that's how you reference an actual enum. So you must be parked to start driving, right? Fairly self-explanatory. So now if I save this, I've got, okay, so it's saying that my function on state mutability can be restricted to view. That's because I haven't done the last one yet. So right now this car is in memory and it hasn't done anything yet. So what I'm going to do is I'm going to write to memory, which is to update the actual car that's being stored in the data of the smart contract. So cars brackets car ID dot status is equal to car status dot driving. And you can see the autocompile stopped complaining. It says, okay, all good now. So previously, when I didn't have this, just demonstrate. See, it says, oh, warning, this shouldn't be public because it's not doing anything that actually writes or updates the state of the smart contract. So why don't you change it to view? That's what it's suggesting. Put that line back in. This line actually modifies the state of the smart contract, so therefore it's saying public is valid. So it's a good thing that you're getting this live feedback from the Solidity compiler. Okay, so it's compiled. Let's deploy this, and we can see here that now we've got add car, drive car, park car, and we have everything. All three functions. Now we can look at the park car function. It's pretty much the same as the drive car function, except that it also allows you to update its new location. So it requires that the car be driving before you park it. It requires you to actually be driving or parking your own car, and over here we have updates to the status of the car, the actual car being stored in the smart contract. So we update the status like we did inside drive car, but then we also update its new lat and long coordinates. So that's great. So now we have these functions. Let's try actually interacting with them. So this is going to be tricky. We're going to have, because this auto-generated UI doesn't give you all the niceties of a full-blown DM. It just gives you the bare minimum. So I'm going to say my car is purple. So what's that? RGB. So FF00FF. Doors, let's say it's got 4. So I'm going to say 0x04. Actually, I think I might be able to put a number in directly for that. Okay, so distance, I'm going to say it starts off with 1,000 on the odometer, and its coordinates are going to be 100, 100, whatever, right? Aha, so we can see over here in action. So it's a require statement. You need at least 0.1 ETH to get a car, right? And you can see that method over here as well. So that's exactly what we want. I'm going to make this a little bit bigger so it's easier to read. Okay, so what we're going to do is when we call this transaction, right, we need to give it a payment, right? So let's give it 0 point, slightly over the required amount, and we press transact this time, and boom. It works. Now, if you're wondering why the transaction was so fast, I'll highlight again that it's all running in a JavaScript VM, so it's completely in memory, not an actual blockchain. It's a simulated blockchain. So there we go. So we've added a car to memory. So now, before we do drive car and park car, let's just look at the state variables over here and inspect them. So we've got num cars, right? And now instead of 0, we've got 1, right? Now, if we have cars, right, we need to pass in a car ID. So if we do car 0, right, we've got nothing, a null value, because there's no car with a car ID of 0. If you do car 1, right, we've got all the values that we input earlier on, right? So the color of the car is purple. It's got 4 doors. It's got 1,000 on the odometer. It's got a latitude, longitude, and a status. So great. You know, that's I guess what we expected. Now, let's drive the car and park the car. So I'm going to drive car 1, right? We press drive car. Okay, so now the car is driving. And then we're going to do park car. So we're going to do car ID 1. And let's say right now, what's the latitude, longitude? It's 100, 100. So let's make it 150 and 200. So driven that distance. Now I press transact, and boom. Now we've updated the car. Now let's requery car 1. So we'll see what has changed, right? So purple for 1,000, 100, 100, and the status is 1, right? So we'll look at it. Status is 1 again. But we'll see everything else hasn't changed except for latitude and longitude, which is what we expect from here. The reason why status is still 1 is because it was changed to driving, and then it was changed back to parked. So there we go. We've interacted with the smart contract through methods. Now we're just gonna trash that because we're gonna recompile the smart contract and deploy a new version because we can't update the code. Code is immutable, remember. So we're actually making a new copy of the smart contract each time we deploy it. Right, let's move on. So we've done functions. Now we'll go on to modifiers. So let's take a look. Aha. So we'll notice over here that we have these require statements over here that are being duplicated. So what we're going to do is we're going to create a modifier that says you can only do this if you own this car, right? And that will be shared so that we don't have to repeat this code twice, like in each thing. So the way we do that is we create something called a modifier, and it's syntactically extremely similar to how we define a function. Modifier. So, oh, caps lock, done that. Type it all over again, modifier, car owner U6. All right, so you'll see so far this looks pretty much the same as a function, except for the keyword, right? So we've got a modifier name instead of a function name. You have a parameter list, just like a function, and you have a function body or modifier body, right? But inside here, what we have is this special syntax called like the underscore with a semicolon. What that means is that when you attach a modifier to a function, which we'll do later on, right? This underscore represents where the actual function code gets executed, right? But this modifier doesn't do anything at the moment. It just simply is a redundant modifier. So let's change that by adding our require statement. So what I'm going to do is I am going to cut this line from the function and paste it here, right? So it says require car.owner is equal to message sender. You may only drive your own car, right? But that is specific to drive car. So let's say I'll change this to you need to own this car, right? That way the message can be reused in both drive car and park car. And the other thing is that we don't have a car, so we're just going to look that up. So we're going to do cars brackets car ID is equal to owner. There we go. So now we have a modifier. Now let's actually use it. So what we're going to do is I'm just going to make it a bit clearer through some white space and indentation. I like to do this when there's more than one modifier. So the drive car now has, we'll add only car owner, right? And that will mean that this car is being called, this modifier is being called, and I'm able to access the car ID from the function parameter list. So if you take a look at this in like what it actually does is what it actually is doing is it's saying when someone calls drive car, it's going to say, oh, only car owner, let's execute that. So then it does this require statement, and if this require statement doesn't throw, then it goes and does this, and this basically executes everything inside the function body. That's what a modifier does. Now that seems redundant if it's only done once, but now we're going to do the same thing over here as well. Simply need to copy this and paste it. So now park car and drive car have both only car owner, and that means that we can delete this. Now we can see that it does the same thing as before. Now the next thing that we're going to do is do the same thing with status. Now this one is a bit trickier because status is the actual content of the require statement is different. So you can see here we're asserting that the value of car status is parked, and here it's car status.driving. So we can't just use the exact same thing in both, right? We have to pass in an additional parameter. So what I'm going to do here in light of time is paste. Just copy this example here. You'll notice that it's the same-ish until we get here. We pass in an expected status, right? And then we have the required statement. Car is not in the required status. So instead of you must be parked to start driving, or you must be driving to park, it'll just say the car is not in the required status. And you should know what that means in each particular case. And so what that means is that when I use only car status over here, in the modifiers, I need to pass in my car ID, right? But I also need to pass in a expected status here. So I'm just going to do car status. So drive car, you need to be parked, right, in order to start driving. and I'll copy that and paste that here, and now we have drawing. Okay, so now we can actually delete the require statements inside here, and we can delete this require statements inside here. Now you'll notice that I'm actually getting a warning here, unused local variable. So thanks, compiler. This is a good thing, right? Compiler is telling you it's not necessary anymore. We were using it previously, but now that we have the modifiers and the modifiers are, doing this, we don't actually need to do that anymore. So we can just go straight. This function is simple enough that we have the modifiers in place. We can just simply execute the state change. And like one thing I'll say about modifiers is that it actually makes the readability, like how easy it is to understand the function, much better, right? So you can see, okay, if I want to drive a car, it can only be done by the owner of the car and when the status of the car is parked. Great, I understand it straight away. I don't actually have to read the function body in order to understand like the logic behind what this function, what the requirements, the prerequisites for this functions are. So that's one great use case for modifiers, like just by eyeballing the function without looking inside of its definition, we already know like a lot more about the function. Previously, we had to look inside the function. All right, great. So I'm not going to bother with a compile and deploy in this thing because it's basically the same as what we had previously. So these modifiers basically are functionally equivalent to what we had previously. So I only care that it compiles correctly. We can test it in the next step. So next up we have events. And this is I guess the most complex thing that we are going to do for this particular tutorial. This is the last step. So thank you so much for staying with me this entire time. Now, roll back all the way up to the top where we've defined our enum. We're going to define one more thing, right? So we have event car honk. That, and we put a semicolon at the end of it, do we? Oh, sorry, it's not with brackets. Yep. So car honk is defined like an event like this, and it kind of works on the inside like a parameter list. What I'm going to do is I'm going to type uint 256 from car. So this is the car that is doing the honking, and then I have uint 256 at car. So what this means is that a car honk is an event. You can think of it as very similar to a struct in that sense. It contains two variables. It contains a list of variables and they're compiled together, but it's a special type because events are designed in order to be emitted inside of Ethereum logs or the logs that are running in the node, and they can be queried in a special way as well without interacting with the smart contract. Yeah, so we'll take a look at that in more detail later on. But before we do that, I'd just like to add the keyword indexed over here. So what that means is that talking about queryability, when the car honk event gets added as a log in the node, we'll be able to see it if we happen to be looking at it at that point in time, but we won't be able to search for car honk events. But when we put index, what that means is that it stores some extra data needed to be able to search for car honk events by the value of from car, right? And then we'll do the same thing as well, indexed at car. And we'll save that. Good, no compiler errors. Now what we're going to do is, in this case, the diffs are quite useful. So we can see here we've got a honk car method that's being added. So we'll scroll all the way down to the bottom, and that's what we want to do. So I'll do that. Type it out in full. So function honk car, and then I'll have my parameter list, and then I will have my modifiers, so public as usual, and then we also have only car owner. So great thing about a modifier, it came in handy for it came in handy already for drive car and park car, and now I'm reducing my need for a third repetition, right? Okay, so that's my function definition. Sorry, my function without the definition, just the name and the modifiers. And we know already that anyone can call it so long as they are the owner of the car. Now, we are going to put a require statement inside here that checks that the car that is being honked at is not a fake one. But realize that I don't have a parameter list. So uint 256 for car ID. So this is the car. This is the owner's car, if you will. And then there's uint 256 other car ID. So the owner of this car is honking at this other car. That's essentially what's happening. Okay, so now we have our require statement. So we have cars, brackets, square brackets, other car ID, dot owner. Right, so this require statement essentially checks that the other car exists. Now the way that it is doing that is a little bit tricky, so we'll go through that step by step. So this cars is a Solidity mapping where the value is a uint 256 and the value is a struct of type car. So this looks up other car and that return value is a struct, right? Now what we saw earlier when we queried a struct from a mapping where that value hasn't been set yet is that everything has 0 values. So let's say we have doors 0. What if a car genuinely has 0 doors? You know, color we can check for a 3-byte hexadecimal value of 00000, but you know, all zeros. But what if that car genuinely was completely matte black? You know, so we've got to think of what is a value that cannot possibly exist, and that's the owner value. It has to be an address, and the address, the 0 address, is a special case which cannot exist. Fun fact: if you want to deploy a smart contract, you send a transaction, but the to address of a smart contract deployment is actually the 0 value. So no account is actually allowed to have an address value of 0. So that's why we do this check over here. We check that the owner of the car has an address that isn't 0, and that's how we determine that the other car does indeed exist. Now you might be wondering, how do I determine that the current car exists, right? And the answer for that lies in only car owner, right? So if say car ID.owner is equal to message.sender, right? You'll notice that this is pretty much the same as this one, right? Except that we've substituted message.sender with address 0. Now message.sender cannot be 0 because it has to come from an account that does exist. So it'll have a non-zero address. So this not only checks that the car that the account that's calling this function owns this particular car, but it also implies therefore that this car exists. Okay, a bit of a roundabout explanation, but we got that. And then finally, we've got the actual event, right? So this is very easy. We do emit car honk, right? And that's the syntax. Now we just got to check it has uint256 for from car and at car, and they're right there in the parameters. Super easy. Car ID, other car ID. And at this point, we have a smart contract that is able to emit an event each time the car is honked. So let's just do that for fun. I know we've already done this before. So I'm going to compile it, no errors, and I'm going to, okay, we don't have any at the moment. Press deploy. So now we have a new smart contract, and you can see over here we have add car, and we also have drive car, honk car, and park car. Now you notice that there are three different colors here, and I'll just recap. So the blue buttons represent like, I guess, query transactions. So if this smart contract were to be deployed to a live blockchain, that would mean that the cars, these functions, num cars and cars, would be when you actually invoke them, it doesn't actually need to send a transaction to a real blockchain. It can just query that locally, right? So you can just do it like that, for example. Right now, it makes no difference since it's a virtual machine anyway. Next up, we have the orange buttons, which are represent functions that require a transaction to be sent to the blockchain. And a red button means that it's also sending a transaction, and because it updates state, but it is payable as well, right? So you can see there in the tooltip, you can see it's payable. This is not payable, and this is just a call. So they're labeled. All right. So let's begin. So in order to honk car, we need to have a car, and we also need to have a car, another car to honk at, right? So we made sure of that. So let's do two add cars. So I'm just going to create a purple car with 4 doors, distance 0 on the odometer, 0, 0, and transact. Right? Yeah, forgot. So let's call this 0.2 ether and press transact. Great. So now I'm going to do use a different account from the one I was using previously. Select that, and this time I'm going to create a red and I have no idea. Let's just make green car. So that's a green car. Let's say this car has 5 doors. It's a hatchback. This car has driven 1,000 kilometers and is maybe 10 meters away from the first car. Press transact. Sorry, forgot to put that value in again. Okay, so 0.2 ethers and press transact. Okay, so now we have 2 cars, and to verify that, I click on num cars, I have 2, and if I press cars, if I do cars 1, I get my purple 4-door car, and if I press 2, I get my green 5-door hatchback car that's 10 meters away. And both of them are status 1, which means that they're 0. And you'll also notice that the address of the owner is different. So car number 2 is owned by an address that starts with 1472, and car number 1 is owned by the address that starts with CA35. All right, so done. We've added 2 cars, and they're on the blockchain. They're on the simulated blockchain. That's the displayed value. Okay, cool. Now what we're going to do is we're going to do honk car, right? So now what I'm going to do is I'm going to do something that I think will result in an error, right? So right now I have the owner of car number 2 selected as my account, and I'm going to do, I'm going to honk at car 1, I own car, I'm pretending to own car 1 and I'm going to own a car, honk at car 2. I press transact and it says you need to own this car because, and that's done by the only car owner modifier. So let's invert that. So I am the owner of car 2 and I'm going to honk at car 1. Press transact. Boom. That succeeded. So now let's take a look at that. Right? We look at the transaction. Right? You can see all the details, transaction hash from and to, so on and so forth. And here's the important part, right, regarding events. So under logs, we can see this over here, and we can see the event. Event is car honk, and here are the arguments. We can see that from car was 2, at car is 1. So we can see from car, at car, it matches up. And we've successfully emitted an event. Okay, so I think that brings us to the end of Solidity by feature. And so far, what we have done is we have deployed to a local virtual machine, right? So what I've done over here is I've got MetaMask set up here with a small amount of testnet RBTC connected to the RSK testnet. I won't go through the steps in this particular webinar because A, we don't have time, and B, it's already been covered in the previous webinar and we have the recordings for that. So please check out our webinars page over here, right? So if you go to developers.rsk.co/webinars, right, you'll see a list of all the webinars. And if you scroll down, you can add it to your calendar. Make sure you don't miss anything. You don't have to manually check. You'll just get reminders. And you can go to our YouTube channel where we have past recordings of all the past webinars. So do check that out when you have time. But for now, I won't go through this. Find the old video. I think it's called Using Remix with RSK. And I'll remix in MetaMask with RSK. So I'll find that. And that will show you how to use the RSK testnet faucet to get some testnet RBTC, how to set up your account to begin with, and look at all of this. So I've done that ahead of time, but right now what it means is that we're ready to roll. We're connected to the RSK testnet via MetaMask, and this is a wallet that allows us to send transactions. So what we're going to do is say injected Web3. So the execution environment has been provided by MetaMask or similar provider. We'll click on that, and what will happen is you'll be asked for permission. Remix Ethereum IDE would like to connect to your account, right? And you're saying, yep, I trust Remix to do its thing correctly. This is not a malicious site or whatever. Press connect. And what happens then is you're not signing any transaction. You're merely telling Remix that I'm allowing this particular web app to interact with MetaMask, right? You haven't actually signed any transactions. It's just like a permissions thing. And the thing you need to check over here is that you should see custom network with a chain ID of 31 that identifies the RSK testnet. All right. Now we're going to do a real deployment. I press the deploy button, and you'll see this pop up from MetaMask over here. So this didn't happen before we pressed deploy because basically it's all virtual. The virtual machine is simulated inside the browser, not interacting with a real network. So you can see contract deployment. You can see new contract. I'm just going to expand that a little bit. So you can see here, look at this. When you deploy a contract, right, you can see it doesn't show you the to address, but if you could see the full detail of the transaction, you actually see the to address of the transaction as being a 0 address, like I mentioned before. And you can see the amount of gas that's been calculated. That depends on the length or complexity of the contract. So you can see that's all that data over there. That's actually the EVM bytecode that was compiled by Solidity.js via Remix. Press confirm. And instead of having an instantaneous, like previously, as soon as we clicked it, boom, it was there already. This time we'll have to wait for about 30 seconds on average for RSK's network, all the nodes that are running on it to mine their transaction or include this transaction in a mine block. While we're waiting, perhaps I'll show you our RSK developers portal. So if you go to developers.rsk.co, I believe the link is here. Yeah, it is. I already put it there. That's our developer portal, and you can check out all the cool information and tutorials that we have on how to work with RSK. So maybe one thing I'll highlight is that we have a quick start over here. Actually, I'll run that on localhost. So we have a quick start over here that will get you up to speed and running with RSK running an actual node. We also have develop, which might be of interest to those of you here. We go to tutorials. And if you're coming from an Ethereum development background, this section here will be useful. And let's see. That tutorial, using Remix and MetaMask with RSK and testnet. So that is actually pretty similar to what I'm doing right now, and I'll go into all the background behind how to set up MetaMask, which I skipped earlier on. Brilliant. So we've got the transaction being mined while we're looking at the dev portal. So we can see over here that the transaction has been mined, and I'm going to take a look at the transaction hash. Copy that, and I'm just going to go to explorer.testnet.co/transaction, paste that over there. Wait for it to find the transaction, and we can see that there's been a contract deployment and that it has been successful. I'm just going to paste this link over here for all of you to look at. And there we go. So you'll be able to open up this page over here. Now, you can look at that. From and to is a special address, like I said earlier on. You can see all the stuff. And here's the important part, right? Here's the contract address, right? So when you click on that, you can see over here, this contract has a balance of 0, right? And it was created about 2 minutes ago. And take a look at the code. You can do that. And I won't go into verifying the contract, but here's the bytecode. Now let's take a look at Remix, right, in the compile section, right? Let's take a look at the bytecode. Just going to paste that here. It's a very, very long thing. So there's the actual bytecode over here. And if you really wanted to, right, and you're following along, you can do the same thing, right? You can compare this value to this value and check that they're the same. But I'm not going to do that now for obvious reasons. Okay, so now we've got a deployed contract on the RSK testnet, and all of you can go ahead and do the same and do the same as well. Like you can interact with this if you've got MetaMask set up and you're connected. You already have the contract. This is the contract. Paste the contract URL here as well, right? And oh yeah, in order to interact with the contract, we'll need the ABI. So I'm going to paste the ABI here too. So if you have the ABI and the smart contract address, which is this over here, then you're able to interact with this on the RSK testnet yourself. So feel free to do that in your own time. Yeah, I think for now we're at the end of the hands-on. So proceed. So if you have any questions, we're available. Please feel free to reach out to us by email at developers@iovlabs.org. I will also mention that our dev portal has a Gitter chat, right? So you can do that over here. Click on that at the bottom and you can ask us questions there as well. So thank you very much. And finally, on a final note, we're hiring. So please get in touch with us at this email address and check out our careers page. Thank you very much.
Thank you, Brandon. Congrats. Very good.
Thank you.
Brandon, very informative. Thank you. Thank you, Mauricio. Thank you, Nacho, also for joining us.